In 1977, NASA took advantage of a once-in-a-lifetime alignment of the planets to send 2 probes to the outermost reaches of the solar system. They sent back the best images and data available at that time about Jupiter, Saturn, Uranus, and Neptune. The program was a smashing success. However, the probes never stopped traveling. They kept going and going, all the while maintaining contact with Earth. They ended up teaching us far more about the solar system than we ever expected. Learn more about the never-ending Voyager program and how spacecraft a half-century old are still performing valuable science on this episode of Everything Everywhere Daily. This episode is sponsored by Fiji Water. You've probably heard of Fiji Water and have seen it in stores. Well, Fiji Water really is from the islands of Fiji. Drop by drop, Fiji Water is filtered through volcanic rock, 1,600 miles away from the nearest continent and all its pollution, protected and preserved naturally from external elements. In this process, it collects a unique profile of electrolytes and minerals, resulting in more than double the electrolytes as the other top 2 premium bottled water brands, giving Fiji Water its smooth taste. Fiji Water's electrolytes are 100% natural, and this water even has a perfectly balanced pH of 7.7. I've recently been trying to reduce my consumption of diet soda, and I found Fiji Water to be a great alternative. Visit your local retailer to pick up some Fiji Water today for your next backyard party, beach day, hike, or even your home office. Fiji Water is Earth's finest water. This episode is sponsored by Quince. I've been telling you about Quince for quite a while now, but perhaps it still hasn't sunk in for some of you just how affordable Quince can be. I went to their website and checked out several prices. A woman's Mongolian cashmere tee, which costs up to $175 from other retailers, is available for just $44.90 on Quince. A men's comfort stretch trench coat that goes as high as $498 on other sites costs only $99.90 on Quince. A European linen chambray fitted sheet set that will run you $270 at competitors can be purchased for only $85.90 on Quince. These are serious discounts on high-end luxury items, and they can do this by working directly with top artisans and cutting out the middlemen. Quince gives you luxury prices without the markup, passing the savings on to you. Keep it classic and cool this fall with long-lasting staples from Quince. Go to quince.com/daily for free shipping on your order and 365-day returns. That's QUINCE.com/daily. Free shipping and 365-day returns. Quince.com/daily. The Voyager 1 and 2 missions have been mentioned in several previous episodes of the podcast. They were first mentioned in the episode on the Golden Record, which was attached to each spacecraft to teach anyone who might find it centuries or thousands of years from now about our world. Likewise, there were episodes on Jupiter, Saturn, Uranus, and Neptune, as well as the Kuiper Belt, which also featured the Voyager missions. As the missions were planned, both Voyagers 1 and 2 were considered a success. Voyager 1 made a flyby of Jupiter, Saturn, and Saturn's largest moon, Titan. Voyager 2 also did a flyby of Jupiter and Saturn, and became the first probe ever to fly by Uranus and Neptune. After Voyager 1's flyby of Saturn in November of 1990, the mission objectives had all been completed. It moved into what was called its interstellar mission. Many of the team members who had been assembled for the program ended up moving on to other things. However, while the primary mission objectives were technically over, the spacecraft were not. While each Voyager probe was sent on a different trajectory, they were each still on the courses set by their gravitational slingshots. Moreover, each of the spacecraft had enough power to last for decades, albeit at varying capacities. So, the first part in understanding how it is even possible for these probes to still be operating is understanding their power sources: radioisotope thermoelectric generators, or RTGs. Each Voyager probe was equipped with 3 multi-100-watt RTGs. They're mounted on a boom extending from the body of the probe to keep them away from sensitive instruments. Inside each unit is 4.5 kilograms of plutonium-238 dioxide in the form of ceramic pellets. This isotope gives off heat as it undergoes natural radioactive decay. The heat is then converted directly into electricity using thermocouples, which exploit the fact that certain metals generate a voltage when exposed to a temperature gradient. If you recall my episode on plutonium, it's almost a necessity for any spacecraft traveling to the outer solar system, as there's insufficient sunlight for solar panels to be effective. Plutonium-238 has a half-life of 87.7 years, which is in a sweet spot for spacecraft. It's long enough that it won't burn out right away, but short enough that it will remain hot for the years required for a deep space mission. If you made a coffee mug out of ceramic plutonium-238 dioxide, it would be able to keep a cup of coffee warm for decades from the heat produced by its radioactive decay. At launch in 1977, each of the spacecraft's RTGs produced about 470 watts of electrical power, enough to run all the instruments and heaters with some margin of error. The process, however, is not perfectly efficient and it degrades over time. The heat decline of the plutonium results in reduced electrical production, and the thermocouples themselves also lose efficiency over time. As a result, the RTGs lose about 4 watts of electrical output per year. As of the recording of this episode, each spacecraft can generate only about 250 watts of power, barely half of what they had at launch. To cope with this gradual decline, NASA has systematically shut down non-essential instruments, heaters, and subsystems to keep the most valuable science instruments and communication systems running. Voyager 1 no longer operates its cameras, which were turned off after the planetary encounters in 1990 following the famous pale blue dot photograph. The photopolarimeter system was also disabled decades ago. Its plasma science instrument was shut down in 1980 after a command issue prevented it from operating, meaning that Voyager 1 cannot directly measure plasma density but must infer it from plasma wave data. Several heaters have been turned off, leaving some instruments to operate at temperatures far below their design specifications. Yet, surprisingly, many of them continue to function. As of this recording, Voyager 1 still runs its magnetometer, cosmic ray subsystem, low-energy charged particle detector, and plasma wave instrument, which together continue to return unique measurements of interstellar space. Voyager 2 has retained a slightly fuller set of science instruments. Unlike Voyager 1, it still has a working plasma science experiment, which made its crossing into interstellar space particularly valuable. Like Voyager 1, its cameras and the photopolarimeter are long shut down, and it continues to operate its magnetometer, cosmic ray subsystem, low-energy charged particle detector, and plasma wave instrument. So the RTG and reduced power consumption is how the probes are able to stay alive. But this then raises the question, how in the world are they able to stay in contact with the Earth? There are two massive problems. The first is that even under the best circumstances, the Voyager probes didn't have a lot of power to work with, and today there's even less. So the strength of the signal is going to be weak. The second is the sheer distance. The inverse square law ensures that the farther away something is when it emits a radio signal, the weaker it's going to be when it reaches its target. That signal degradation isn't linear either. When you double the distance, it becomes a quarter the strength. And when you triple the distance, the strength of the signal is only 1/9 of the original signal. Voyager 1 is currently 168 astronomical units from the Earth, with an astronomical unit being the average distance from the Earth to the Sun. Voyager 2 is 140 astronomical units. Or to put this another way, a radio signal traveling from Voyager 1 to the Earth at the speed of light currently takes 23 hours and 19 minutes, almost a full light day away, or 15.6 billion miles. Voyager 1 is currently sending radio signals with about 20 watts of power. By the time it reaches the Earth, that signal is less than an attowatt, or a billionth of a single watt. The way we can communicate with the probes is via NASA's Deep Space Network. It consists of 3 main facilities spread evenly around the globe: Goldstone in California's Mojave Desert, Madrid in Spain, and Canberra in Australia. The locations were chosen so that as the Earth rotates, at least one station can always see a given spacecraft. Each site has multiple radio antennas, including massive 70-meter dishes capable of detecting signals that have weakened to a tiny fraction of a billionth of a watt by the time they arrive from interstellar space. The Deep Space Network antennas amplify and decode these signals, then forward the data to mission controllers at NASA's Jet Propulsion Laboratory. As the distance has increased and signal strength has decreased, the data transfer rate has declined as well. When Voyager was near Jupiter in 1979, it could send back data at over 100 kilobits per second. As the probes receded and the signal weakened, engineers stepped down the transmission rates. Today, Voyager 1 typically sends only about 160 bits per second, which is slower than the baud rates of early modems from the 1960s. The trick that makes this possible is extreme efficiency. The science instruments send back very small packets of data, which are carefully encoded to correct for errors caused by noise in the faint signal. Beyond the power and distance, there is another problem. The Voyager probes are simply old. While the Voyager spacecraft were launched in 1977, they were built several years before that, which means that it has 50-year-old computers on board that are controlling everything. The processing power in the key fob for your car is literally much more powerful than the Voyager computers. Their computers were custom built with 1970s logic circuitry, plated wire memory, and handwritten assembly code. By the 2000s, it became necessary to reprogram the probes to keep them functioning. But there was a huge problem. Almost no one at NASA was still familiar with those systems, and documentation was often incomplete or scattered about in old binders. Many of the original Voyager engineers and programmers had since retired, and they were the only people with the specialized knowledge to rewrite and test code safely. NASA literally called them back to consult, teach, and in some cases, even hand code new routines. For example, Voyager 1's thrusters used for altitude control had degraded. Engineers decided to fire backup thrusters that hadn't been used since 1980. To do this, NASA had to rewrite code and recompile old command sets. Retired programmers were consulted to understand how to properly issue those commands without risking the corruption of the memory. The effect worked, and Voyager 1 successfully switched thrusters after 37 years. So, what exactly have we learned since the Voyager probes ended their primary mission? Since Voyager 1 crossed the boundary into interstellar space in 2012, followed by Voyager 2 in 2018, both spacecraft have given us our first direct look at the environment beyond the sun's protective bubble. Their instruments have shown that the interstellar medium, just outside the heliosphere, is denser than expected, with Voyager 2's plasma sensor detecting particles nearly 40 times denser than what had been measured inside the boundary. Both spacecraft have confirmed that cosmic rays from the galaxy are more intense once the sun's magnetic field no longer deflects them, offering a clearer picture of the radiation environment between the stars. They have revealed that the heliosphere itself is not a smooth bubble but a dynamic boundary, influenced by the solar wind pushing outward and the interstellar medium pressing inward, creating a fluctuating region of magnetic turbulence. Voyager 1's plasma wave instrument has picked up faint hums from interstellar plasma oscillations, essentially giving us the first sounds of the galaxy's background activity. Together, these findings have reshaped how we think about the sun's role in shielding the solar system, provided crucial data for models of cosmic radiation that affect future deep space travel, and begun to map the transition from our stellar neighborhood into the broader Milky Way. So, what does the future hold for the Voyager probes and their seemingly endless mission? Despite the exemplary job NASA has done keeping these spacecraft alive for decades, all things must come to an end. The power the RTGs are producing will keep decreasing, and the distance to the Earth will only keep growing. More and more systems on the probes will have to be turned off in the coming years to maintain sufficient power for radio operation. The cosmic ray subsystem on Voyager 1 may have to be turned off this year. The exact date isn't known, but it's estimated that sometime between the next few years and 2036, the probes will no longer be able to communicate with Earth, and their mission will be officially over. Almost 6 decades after it began. Neither probe is heading anywhere special. Voyager 2 will pass within 1.7 light years of the star Ross 248 in about 42,000 years. Voyager 1 should reach the Oort cloud in about 300 years and take about 30,000 years to pass through it, giving you an idea of just how big it might be. In 40,000 years, it'll be about 1.6 light years from the star Gliese 445. Both probes will coast through the Milky Way for millions and possibly billions of years, carrying with them the golden records, which serve as a symbolic reading to any intelligence that might encounter them. In that sense, their mission will never truly end. It only shifts from an active scientific exploration into a passive, almost archaeological role as the first emissaries to the stars from the planet Earth. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Austin Oetken and Cameron Kieffer. My big thanks go to everyone who supports the show over on Patreon. Your support helps make this podcast possible. And I also want to remind everyone about the community groups on Facebook and Discord. That's where everything happens that's outside the podcast, and links to those are available in the show notes. As always, if you leave a review on any major podcast app or in the above community groups, you too can have it read on the show.